Hello, welcome everybody. My name is Dmitry Polyakovsky, and I'll be speaking to you about caching. And I'll cover internal caching, distributed, and semantic. I work at Oracle. I'm a lead engineer on a project called OCI Cache. We offer managed Redis and Valkey. If you're not familiar with Redis and Valkey, Redis is an in-memory database that's often used as a cache, but it has a number of other use cases. Valkey is a fork of Redis that happened about 2 years ago due to some licensing issues. I actively participate in the Valkey project by maintaining a special SDK that allows you to build modules or extensions to Valkey, and this SDK supports Rust programming language. And if you're interested in that, please come talk to me afterwards. If you're interested in our service, OCI Cache, you're welcome to check it out. You can create cache clusters. We support Redis and recent versions of Valkey. And we have a lot of cool features. And our product manager is here if you really want to know more details. You know, they say there are two hard problems in software engineering. And number one is naming things. And number two is cache invalidation. So we're going to talk a lot about cache invalidation. Okay, that's a joke, you know, off by one counters. Yeah. All right. Well, first a quick survey. How many people use just internal in-memory caching? Okay. Any specific libraries? Guava, Caffeine, just hash map? Okay. How many people use distributed caching? Redis, Memcache, D, coherence, anybody? Okay. We get a lot of questions about coherence because it's an Oracle product, but it's outside the scope of my team. And how many people have heard or tried semantic caching? Okay, so we're actually going to spend most of the presentation in that. So I hope you'll learn some interesting stuff. Let's start with simple, internal caching. Concurrent hash map, we implement simple get, set, delete methods, easy. If you want something a little bit more feature-rich, Guava, Caffeine, really fast. The data is like literally on the CPU sometimes. Caffeine claims like nanoseconds response times. And here's how it works, right? We don't want to query the database. It's slow, it's expensive. Our DBAs are unhappy. We run that query once. We generate the data, we store it in memory, we retrieve it from there, we specify the TTL or time to live. After the TTL is passed, the library will usually automatically purge the data from cache, and the next request will have to go to the database. So easy way to scale the system, but we are making a trade-off because data in cache will frequently be out of date with the source of truth, the database, or a third-party API. Okay, so pros, fast and easy to implement. And the nice thing about in-memory caching is you don't need to run additional infrastructure. You don't need to spend money on it. You don't need to have dedicated engineers maintaining that infrastructure. But the biggest downside of in-memory caching is that you will have different caches on different servers. So if server 1 runs that query right now, gets particular values from a database, does the calculation, it'll cache that. But server 2 may be hit sometime in the future, and by that time, the data may change. If it's not a problem, go with in-memory caching, but sometimes you need the data to be the same. Another downside with in-memory caching is that usually those libraries don't offer any persistence options. So if a server restarts, data is lost, meaning all the queries will again have to go to the database. Not a problem if only one server in the fleet restarts, but if you have a massive restart and every server has to then hit the database, could be an issue. And frequently, these libraries don't have a lot of operator tooling to help you view the contents of the cache directly, or flush cache. How many people had a situation where they cached something incorrectly and had to quickly flush cache? I'm sure everyone had. All right, quick demo. So I built this very simple application, and I'm going to have here Caffeine cache. So let's type some kind of a unique ID. Run lookup, so I'm essentially sleeping for 5 seconds, and that's my slow computation. So you can see the data came back, and now each subsequent lookup is much faster. And by default, I set my TTL there to 60 seconds. Let's look at the code behind the scenes. I have this simple Caffeine controller. I'm using Micronaut framework for this application, so it gives me a lot of nice features. And I'm also using the Caffeine library. So here's my URL, Caffeine, and then I get data by ID, and I just sleep for 5 seconds. And all this cache config that's provided by Micronaut. So it's super easy to build. And I created configuration here where basically I created this called Caffeine default cache, which I reference right here. And all the data will be stored in that cache. And Micronaut has a really cool feature, expire after write, meaning that's how long the data will persist. And that's pretty useful for cache, right? It also has this ability to record stats. So if I go, by the way, is my mic okay? I keep hearing weird echo. All right. So here, for example, I have this different URL, and it gives you metrics. All of this is provided by Micronaut frameworks, and I can, for example, look at see how much cache I have one value in cache. So this could be useful for some kind of a monitoring tool. All right. So the pros of Caffeine, it's going to be really fast. It's easy to implement. You can control the size. The biggest downside to me, of course, besides, of course, the ability to persist data, is that, to my knowledge, you cannot control the expiration on a key level. Because some keys you may want to keep for a minute, some may want to keep for an hour. And the only way to do this with Caffeine is simply create 2 different caches. So it'll be like Caffeine default and Caffeine long duration and others. And then in your code, you simply annotate it with appropriate cache. So you essentially have groups of caches, like short-term, medium, and long-term duration for your caches. Possible, doable, but less flexible than ability to specify it for each key and value. Okay. Any questions so far about Caffeine? Okay.
Maybe the font.
You want it bigger? Which font? The IDE font or the browser font?
The ID.
IDE?
I don't know.
Can folks see from the back? Good? All right. Let me know. But thank you. Okay, so now let's talk about distributed caching. I will primarily focus on Redisson and Valkey, but there are other technologies. Oracle, for example, has a product, Coherence. There is an original solution emerged about 20 plus years ago, Memcached. And there is, for example, EHCache. The interesting thing about EHCache is you can cache both in memory, but also have these shared servers, Terracotta, where your cache will be held as well. All right, how many people use Redis or Valkey? What are the use cases? Caching, message broker, job queue, rate limiter, lock management. Okay. So the biggest advantage of using distributed cache is that you will have the same cached across all your servers. You will also have better durability. Redis and Valkey support different options. You can use replication, where you will dole your writes to the primary node, and then you can have many replicas. For example, at OCI cache, we support up to 4 replicas per primary. So you get a lot of durability, and you also have a lot of read scalability, because you can do reads from replicas. The only caveat is that replication is asynchronous, and what we're seeing is that like fraction of a second replication lag. So if that's acceptable to you, you can really scale things. You also have ability to scale with sharding. So data will be split across multiple shards, what Valkey calls cluster mode. And we have potentially, like we support, for example, up to 100 nodes per cluster mode. And each node can have up to 500 gigs. So you can have, let's say, 25 shards. Each will have 4 servers, 1 primary and 3 replicas. And up to 500 gigs, we're talking about terabytes of data stored in RAM. And we actually have customers who are storing many, many gigabytes, hundreds of gigabytes in RAM. And they're using both in sharded and, but that is more common with a sharded mode, because with the non-sharded mode, you usually, well, you can store about 100 gigs. Well, you can store theoretically 500 gigs, but that's less common. Anyway, you also have something called Valkey CLI, and that allows you to get inside Valkey process and look at the contents of the cache directly and potentially delete some or all of the keys. And as I mentioned earlier, what I like about Valkey is that it's a very multi-purpose technology. You can start using it as a simple cache, then start using it as a job queue, then do session storage, and so on. Maybe it's not as good at every one of those, those feature areas, but it's pretty good, and it's simpler to have one technology. The downside is, of course, latency. You will need to make that trip from the server to the cache. And you will have to either run that infrastructure or pay for service. Now, you know how I said that there's a downside of latency? Well, I was not entirely correct. because Valkey supports something called client-side caching. And you truly get the best of both worlds here, that you will have in-memory cache, and then you have a distributed cache. And those are separate from your source of truth database. So what Valkey does is it'll keep track of which client requested which key. And when the data in Valkey is deleted or updated, it will send invalidation message to the appropriate clients. And I will show you later Redisson library. And Redisson supports integration with Caffeine. So it makes it much easier for you to implement this functionality. Now, the biggest downside here is that to track all this metadata requires memory. So you might have to make some trade-off choices about how many keys you're tracking, and maybe instead of tracking each and every key, you only track keys by specific patterns. But there's really good documentation on Valkey and Redis websites. They both support this feature. You can also run Valkey just on a local host. You'll get really good latency, like microseconds. Not as fast as Caffeine, but still faster than milliseconds that it will take you to go from the application server to the distributed cache. And you'll still have reasonable durability because you will be able to take advantage of Valkey's own either AOF or RDB persistence. And actually, one of the first systems I built using Redis, I used Redis as an advertising cache. So I had my advertising server and a local Redis, and I had a whole bunch of servers. But what I had to build is I had to build a separate process that made sure that the cache is the same across all of those servers. And we basically like monitor the main database and kind of push data. But what was really nice is we could reboot any of these ad servers and not worry about the hit to the main database. If you're running Kubernetes, you can run Valkey cache. In fact, for our control plane operations, we're using a very simple Kubernetes pod running a very small Valkey cache. So we're using cache to scale our caching system. It's simple, especially if you don't care about persisting data, because Kubernetes will recreate your pod. But unless you implement something called persistent volume claims, data will be lost. So if you don't care about it, and if you only need to store, let's say, a few megs of data, very easy to get started. However, if you want to scale it to tens of gigabytes, there could be challenges. And of course, my favorite way of running Valkey is to use a cloud service. At OCI Cache, we take care of all the monitoring for you. We take care of monthly security patching. We allow you to increase or decrease memory, just like with a few clicks. And we give you an option to do zero downtime upgrades, so from, like, let's say, Redis to Valkey. And depending on your library of choice, you will have slightly different features. So if you want something lightweight, go with Redis. If you want kind of middle of the road, Redis. And I personally like a library called Redisson. By the way, they both work with Redisson and Valkey. And on Valkey website, there's actually a specific Valkey-specific officially approved clients. But almost all functionality will be available via any of these libraries. And depending on your framework, you may have even a higher level abstraction. So I know Spring has some Redis integration features, and Micronaut and Drop Wizard all have additional libraries. But under the hood, they all use pretty much one of these. Okay. What I like about Redisson is that in addition to giving me the ability to access the native Redis data structures, it also gives me more complex abstractions. For example, if I want to implement a rate limiter, that requires creating several Valkey keys. And Redisson makes it really easy for me. I will show you later. It's just 3 lines of code, and I have a basic rate limiter that is shared across multiple application servers. And I'll show you this Redisson client interface. Very easy to get started with. Okay, demo. Oops. Okay, so here I have a Redisson cache. So as I said earlier, with the Redisson Valkey, I can specify TTL per key. So let's say we want to say foo and TTL of 30 seconds. So I'm doing the same thing. I'm sleeping for 5 seconds to generate this data. And you can see here that it came back, and I just gave it a unique timestamp. So now, or at least for the next 30 seconds, these responses are going to be very fast. And if I create a different key, again, it's performing the computation. Data will come back, and now it's fast. And all of this data would be available to other web servers in my fleet. Rate limiter. With rate limiter, you can specify a couple of options. You can specify the rate and the time interval. So here, and of course, the unit of time. And you can specify whether you want the overall rate limit or per client. If you need to implement per client rate limit, you actually don't need to use Valkey because the data will be like held per each client. And I personally don't like that approach because if I change the number of clients, the number of servers in my fleet, that means that I'm increasing my rate limit. If it's 5 per server, right? It depends on how many servers I have. So I frequently have some other downstream system, which is why I'm implementing this rate limit. So I really think overall is what you want. So here's really simple. I'm going to specify, let's say, limit 1 and 5 per 10 seconds. So I hit it. Okay, so it comes back with true. Hit it again, hit it again, hit it again. Oh, now it's false. So now I'm locked out for the next 30 seconds for limit 1. But if I say limit 2, see, this is true. Yep, and now this is false as well. So, is there a question? Okay. Yes, of course.
So this is the cache.
Yes.
You limit the rate. Like,
It will stop whatever your execution needs to stop. Let's say you want to control how frequently people access your API.
yeah.
You have a bronze, silver, and gold service plan, right? Bronze allows you to take 10 requests a minute, bronze, silver, different white. So what you do is that you have some kind of a customer ID that they pass in their request. So you simply look at the customer and you say, oh, this customer is allowed to do 10 requests a minute. And you take the customer ID as your limit key.
Yeah, okay, cool. So the use case here is not the data cache. It's
Yeah.
the
Yes.
API gateway.
Exactly.
Just for the rate limiter. Right?
Mm-hmm.
Okay.
But I'm using the same technology and the same library. Yes. Think of a Redis or Valkey as both a cache and a rate limit store. So if you really, really care about speed and you have a fixed pool of your servers, then you can do the calculations and say, well, I can allow this many requests. However, if we get back to the same customer that's only allowed, let's say, 10 requests a minute, unless you hit, let's say you have 10 servers, it means you can only do 1 per server, and then you're guessing that the requests will be evenly distributed, which is extremely unlikely to happen. So it's better to have rate limit centralized. It will create Valkey to be a central point, right? So all the requests will have to go to the same thing. So if you're using Redis or Valkey for both caching and rate limiting, what you can also choose to set up different clusters or different servers. So one will be used just for caching, and you will scale it appropriately. A different one will be used just for rate limiting. And you can also maybe, if you're really concerned about scale, you can go with a cluster mode. Again, yes, there was a question.
A light bulb just like you actually use it as a semaphore.
Yes, there's literally a functionality for semaphore in Redisson library. The question was, or the comment was that you can use Redis or Valkey as just a shared storage for different things. Any other questions? No. Think of them as interchangeable. Valkey is a fork of Redis. So basically 2 years ago, Redis changed its license. In response to that, Oracle, OCI, AWS, and other cloud vendors basically forked Valkey, Redis 7.2. So that you will see there's a version of Valkey 7.2, and that kind of emerged. So at this point, so there's Redis 8 and there's Valkey 9. There's a lot of compatibility, but the Redis and Valkey are starting to introduce slightly different features, unfortunately. But most libraries will work with either or. So, but obviously for production test. Yes. Oh, sorry. Yes. Hobbits, let me show you the code, and then I'll answer the next question. So here I have this Redisson controller. So you'll see here for caching, again, very similar. I accept some parameters. I create a hash just to create a unique cache key. And then I'm using this Redisson client. I get map cache. If I find something in the cache, I return it. If not, I do my computation and I store it. And I can specify different TTL for different keys. I found that to be very useful. But the rate limit, so literally it's 3 lines of code thanks to the Redisson library. I set rate limit I give it a name. I set its rate and type, for example, overall 5 for 30 seconds. And then I try to acquire a limit. And it just comes back true or false. There are several Redis Valkey data structures behind the scenes that come into play But from the Java point of view, just think of it as these 3 lines. And you have ability to, let's say, limit a customer who has exceeded their rate limit for a period of time. Again, this is where those TTL per customer, so you can have 1 minute, 1 hour, 1 day, or whatever. Let's see. There was a question. So MySQL and MariaDB reversed? Oh, because Maria was the later fork. Yeah. So anyway, yeah. But just, if for most use cases, Redis and Valkey will be interoperable. But like I said, there are some new features being introduced. And libraries will also be interoperable. But like I said, as often happens with forks, with time, they really start to diverge. I'm using the latest version of Redisson, and it's fully compatible with Valkey. You have to really look at which language, which library, and so on. You can look on Valkey website where they have the officially approved Valkey clients in different languages. Yeah, exactly. So if you're using Redis and you have, let's say, an older version of Redis, what I would recommend is going to the latest version of Redis and then testing that version of Redis against Valkey. In fact, I believe Valkey official Java client is based on Redis. So yeah, you're absolutely right. If you have a bunch of Redis on specific code and you want to go to Redis, you will lose a lot of functionality. Okay. So, okay, good questions. Thank you. All right, so now let's talk about semantic caching. So let's summarize a regular caching first. So with regular caching, again, we get that input, we hash it, we generate the unique ID, we check the cache for exact match to that ID. If found, we use it. If not found, we do the work. We store it in cache with a TTL, and then we reuse it on subsequent requests. And data will look like this. So you have a key and value with TTL, and a different key, different value, different TTL. Before we dive into semantic caching, I want to cover several topics, and you will see a lot of math. And it's important to really understand these concepts, because with caching, traditional caching, we kind of think of it as in terms of one dimension. What is the TTL? So for example, if we were to query an API and ask for weather in Redwood City, we would get this data and we may choose to cache it. But for how long? 5 minutes? Fine. An hour? Fine. A week? I suspect the weather will change, and while our application will return it, our customers may be unhappy. So with semantic caching or semantic search, we have a kind of a second dimension, a concept of similarity. So in the case of weather example, if we, let's say, didn't have weather in Redwood City, but we had weather in San Mateo, we could probably substitute one for the other. Well, if we didn't have San Mateo and went to San Francisco, well, San Francisco actually has microclimates, so maybe that's not good enough. Or maybe it is. But if we don't have San Francisco and we go even farther to, say, Los Angeles, that's probably not good. And that's where this concept of similarity threshold comes in. Again, how close? Because in semantic search, we're looking for semantically similar. So again, just think of it as TTL and similarity as 2 dimensions. And the farther you go in time, the less reliable your data is, and the less similar you set your similarity threshold, also the less reliable data becomes. But if you get it right, you can really save yourself a lot of time and money, because just like we protect our databases with cache, because databases are these very precious resources, frequently they are under a lot of load. LLMs are also very expensive to make calls against. And we want to make our DBAs happy with regular caching, and we want to make our CFOs happy with semantic caching by not abusing LLMs. And we do it as we leverage semantic search, where we compare not the exact match, but the meaning. And to get that, we take the input and we vectorize it. So we'll actually have to call an LLM to create a vector. But vector generations with LLM is very cheap compared to running inference queries. And then once we get the vector, then we'll start comparing vectors. So vectors, they have magnitude and direction. So here's 2 vectors in a two-dimensional space. So we have x, y, and we can literally tell they're similar. They're pointing in the same direction. They're comparable size. Here we have 2 orthogonal vectors, and we can see how they are less similar. And here we have 2 opposite vectors. Well, in the real world, we're going to have hundreds or thousands of dimensions, and our vectors will look like this. So what vector similarity search is, it goes through all these numbers and compares them all and finds similarity. Now, how do we compare the vectors? So we can use several approaches. There's something called cosine similarity, where we compare the angle, right? So here we can see that the cosine of this angle is close to 1, and cosine is adjacent over hypotenuse. In case of orthogonal vectors, the angle will be close to 90 and the cosine will be close to 0. And in case of the opposite vectors, it will be -1. Okay. Another approach is to use Euclidean distance, where basically Pythagorean theorem says x squared plus y squared equals z squared, right? So here's the coordinates. We do the calculation, and we get the exact length of this vector. But it is an expensive computation. And one thing we can easily do to save ourselves cycles, we can just avoid taking the square root. Because instead of comparing the square roots of these numbers, we can just compare the squares, right? Because at the end of the day, we just want to know who is most similar. But what this does, this compares the actual distance, except not in 1 dimension, but in 2,000 dimensions. No, in 2 dimensions, but in, let's say, 2,000. And another approach is called inner product. So where we take the components, we multiply them, and we sum the results. So here I have vectors A, B, and C. So A and B comparison is 11. A and C comparison is -17. And you can just kind of like visualize it that it's going to be in the opposite direction. So obviously A and B are much more similar than A and C. And what we're measuring here is that if the vectors point in the same direction, you will have a larger value. Okay. Another interesting concept is a concept of normalized or unit vectors. So what we do is we shrink the magnitude to 1. So here's a vector, 3 by 4. We can easily calculate the size to be 5. What we do is we shrink the size to 1, and we divide all of those dimensions by 5 as well. So this blue vector is 0.6 by 0.8. Questions? No? Okay, I'll keep going. Yeah, yes, go ahead.
I didn't get the concept of how did you, so 3 and 4 getting 5.
Yes, 3 square plus 4 square, square root is 5.
But the 0.6 part, I couldn't.
Okay, so we know the magnitude is 5. So we divide 3 by 5, we get 0.6. We divide 4 by 5, we get 0.8. And 0.6 square is 0.36, 0.8 square is 0.64, sums to 1. Okay, the interesting thing about normalized vectors is that their inner product is actually equal to cosine similarity. So here's some more math. So basically, let's say we have a vector that's 1, 0, it goes like this. And a vector that's 0.7, 0.7, goes like this at 45-degree angle. So here's the math. It comes out to be 0.7, and cosine of 45 degrees is also 0.7. So all of these are important because they will help you save computational cycles when you're doing those searches. And you can specify them. I will show you later how to do it with the Redisson library. Okay, so cosine compares angles, inner product compares directional alignment, and L2 calculates actual spatial distance. So the next question is that, well, we don't need to compare 2 vectors. We need to compare millions of vectors because we have our original vector, right? And we have to go through a whole bunch of vectors we have in our vector DB to find the closest possible match. We can use brute force, but for obvious reasons, that's not going to scale. So approach that's often common is called hierarchical navigable small world, and we'll refer to it as HNSW. And what you want to do is you want to find approximate nearest neighbors. So it's a graph with many layers. And it's useful when you have to have like millions of vectors, and each vector will have potentially thousands of dimensions. By the way, all vectors in a graph will have to have the same number of dimensions. And you essentially have log n time complexity. So how does it work? Think of it as like layers. So the very top layer is going to be the most sparse. It will be the fewest number of vectors and fewest connections. And it's kind of like a highway system. You can get where you're going fast, but you're not near where your final destination. The middle layers are like the major roads in a city. So they'll get you closer because, and again, there's more vectors there, there's more connections. And the bottom layer is where all the vectors reside. And it's going to be the largest layer. And it's like local streets. So you'll get exactly to your address. but this is what's going to cost you the most memory. But the more layers you have, the more memory you'll need to use. And the more vectors you have, the more layers you will need to create. So if with 10,000 vectors, maybe it's 4 or 5 layers, but with 100 million vectors, it could be as many as a dozen layers. And what's taking up the most, and the way it works is that basically you will choose the random node at the top. You will find the closest match within its neighbors, usually 16 neighbors. Then you'll go to the bottom, the next layer. You'll do the same search and repeat and repeat and repeat. So here's the visualization. You start here. You go to this. You drop to one level below. You search its neighbors. You find this. You drop to the next level. You search its neighbors, and so on. And eventually you land here. So log n versus n. Yes? Question, is it similar approach as B-trees? Yeah, similar, but this is a graph, right? So 16 neighbors. Keep that in mind. Okay. So it's going to be much faster than brute force, and it's going to be pretty darn accurate. But it's going to cost you memory. Okay. The biggest usage of memory is going to be the number of dimensions. So here's some basic math. If each dimension is a float 32, that is 4 bytes. When I was preparing for this presentation, I used a model called Tiny Llama running locally, and it wasn't very good. And it used 2,000 dimensions. I then downloaded a different model called Llama 3.1, and it has 4,000 dimensions. And if you use some, like let's say OpenAI, you can actually control the number of dimensions. You can go as little as 16. So it's very easy to visualize, and it's going to require a lot less memory, and your search is going to be very unreliable. So, but with 4,000 dimensions, you're going to have 16 kilobytes for each vector. On top of that, you're going to store the graph connections. So if 16 neighbors, 8 bytes, 128 bytes, and then some overhead. But again, you can easily see that if you're storing, let's say, 1,000 vectors, that's 16 megabytes. 1,000,000 vectors is 16 gigabytes in the bottom layer, and then more at the top and top. And then again, the more vectors, the more layers. So be very mindful of your memory usage. How you store it, for how long you store it, really matters. Okay, just to summarize, for small data sets, you don't need it. You can just go brute force. For large data sets, there's other approaches called inverted file index and product quantization, and they make some trade-offs on how they store things to compress on memory. And that may impact your accuracy. Okay, let's try to put all this together. So let's pretend we have a user typing, "What is machine learning?" as a prompt. We will call an LLM to convert it to a vector. That is an LLM call, but that's a cheap LLM call compared to the running inference call, which we're trying to avoid. So now, once we have this vector, we will then compare it to a vector database, which happens to be Valkey, with Valkey search functionality. And let's say we have ML definition, which has 0.94 similarity match. That's pretty similar. We then check for cache, and if we have the cache corresponding to that vector, we use it. Fantastic. We responded very quickly, and we saved money. If we don't have cache for that vector, then we have to query LLM. But let's say we don't have this ML definition stored. So what do we do then? Well, we specified similarity of 0.90 minimum and match found with 0.94. But if we don't have the 0.94, we either query LLM or we can optionally lower similarity threshold. So let's say we lower it to 0.75. Deep learning will match it. Deep learning, machine learning, kind of similar. But let's go even further. Let's say we don't have deep learning and we lower the threshold to 0.5. Well, in that case, we get Python basics. And we can tell that Python basics and machine learning are not that similar. So as I said, the lower the similarity threshold, the more likely you're going to get stuff that's not useful. Yes?
Your threshold is a configuration. You're not changing it on the fly. You're just talking about it for the purposes of this slide.
You would have to specify it in a request. Not at the index. Like index is created, vectors are stored. Certain things you will have to define during index creation. For example, the cosine similarity search, the float 32, etc. I'll show you later in code. But other things can be specified for each request. So you could have logic in your application that says, well, if you didn't find anything for 0.9, let's try for 0.8. But that will require additional search, not LLM call. Yes?
Basically, the previous count are the keys in the cache. So ML definition would be a key in your cache.
Yeah. Well, it's not a key as far as the Valkey key is concerned. It's actually going to be stored a little differently, but it's a match. It's equivalent of the hash of the string. But if we hash the string in regular caching, we have to have an exact match. When we vectorize input, we can have this similarity match. Yes?
If you had suggested 0.7 for this
Sure.
specific query, which one would you have gotten? Deep learning or ML definition?
You would have gotten potentially several of them, and then you can filter them out client side.
Can you sort them?
Yeah.
Okay.
Yeah.
So the similarity comes back as well.
Yes, yeah. You will see in code that similarities can be returned. Okay.
So the key is the vector, right? How about the
As far as Redisson and Valkey is concerned, we actually have a different key, which just happens to be a hash string. But I'll show you later how data is stored. Basically, you have like ID, and you have vector and cache content.
but the value is really the text, right?
The value is the cached content returned from the API call. So in this case, whatever. You trust me, you're going to like the demo. All right. So just to summarize it, we vectorize the input, we run VSS. If we find a match, we look for the cache. If we don't find a match, we query LLM. And if we don't find a match, we then have to query LLM and store it. So the question you need to ask yourself is, how long do you want to store the vector if there is no corresponding cache? Because a vector without its cache is not that useful because you're going to have to query LLM anyway. And vectors are expensive in storage, 16 kilobytes. So you can choose to set expiration on your vectors to be the same as your cached content and just kind of flush them both, or you can choose to treat them differently. And to store this, you have also several approaches. So here, for example, I'm actually creating two different key patterns. So I'm creating key with the prefix doc, and let's assume that key 1 is just a hash, some kind of unique ID. And then I actually store a vector here. And then I have a key with the prefix cache, and I have the value and a TTL here. So it's two separate keys. I'm going to waste a little bit of memory storing them as keys separately. Very small percentage of the vector. Like, again, this is 16 kilobytes. The cache value could be potentially megabytes. So a little bit of memory wasted for storing keys separately from cache. So vectors separately from cache. Not a big deal. And it gives you a little bit of flexibility. Another approach is that you store them all inside the same Valkey hash map. So now you just have one key, and inside that hash map you have key value pairs. So it's a hash map of hash maps. So then you store your vector, you store your cache value, and in recent versions of Valkey, there's a cool feature called hash field expiration. So you can define TTL not at this layer, but at this layer. So you can let Valkey expire them after whatever you tell it to. If you don't have that, you can store the expiration time, and then in your application, you can make the decision. And you can also store the input as just for reference. Yes?
But you're in the TTL val 9 feature, you're still ejecting the entire key, not just the cache.
No. So Valkey 9 and Redis 8 have this cool feature called hash field expiration. Okay. So again, you have a key here and you have a whole bunch of key value pairs, and you say just expire this or this at different times, but leave the main hash map. Okay. So yes.
In option 1, there was a dot. What is dot?
It's just a prefix. Yeah. So basically, I'll show you later when you create this. Yeah, when you create the index, you can specify the prefix, and you can specify. So the index will not, for example, you don't want to index your cache keys. You only want to index the keys that hold the vectors. So the one way to do it is with a prefix. And then when you specify the index, you can choose to tell it only index these specific attributes inside the hash map. Like I said, you don't want to index the cache. You want to index the vectors. All right. So again, why does this matter? We want to save money. LLMs are expensive. And in case of agentic architecture, where we have multiple agents and each has its own LLM, we want to prevent these unnecessary LLM calls. Because I'm fully expecting people will start using AI, and then there'll be huge bills to the companies. Okay. All right, so another advantage of semantic caching is that we're essentially using our commodity hardware for caching to cache this data and not have to run inference on the expensive GPU or TPU hardware. We're going to get much better latency, and we can scale. The biggest downside is you really have to be careful with accuracy. Okay, so here's some quick numbers. The embedding generation, the very first LLM call, is much, much cheaper than actual inference. So you can look up for different service providers what it costs. And you don't want to use semantic caching in certain situations, particularly where you have very sparse data set. So again, if we go back to the example, if we have like, let's say San Mateo, Redwood City, San Jose, that's fine. But if we had like Los Angeles, Dallas, Seattle, and New York, that's probably very hard to make predictions about the weather. Yes?
So this is a fairly new, right?
Yes.
Valkey and Redis have the same semantic cache.
So Valkey, okay. I'm going to skip to the next slide here. So again, so Redis has this thing called Redis Search, which was originally implemented to support full text search, like almost 10 years ago. Later, they added support for semantic or vector similarity search. Valkey Search emerged about a year and a half ago, shortly after the Valkey project. And they started with Valkey Search first, Vector Similarity Search first. And literally, they just dropped the release this week, and it has a lot of full text search capabilities. So if using certain libraries like LangGraph, LangChain, they were primarily designed to work with Redis and Redis Search, but they should work with Valkey and Valkey Search. Okay. All right. Perfect. I talked about the Valkey Search. So again, the biggest advantage of it is that you're essentially treating your Valkey as both the vector database and a cache, and you can choose to purge those vectors when you no longer need them, and you can choose to purge cache content when you don't need it. The biggest downside is it could get expensive, and you have to have access to the server to run this module, because it's essentially a dynamic library. So either you have to run your own infra, or use a cloud vendor like OCI Cache, where we support it, or another cloud vendors, they support it as well, and you can start taking advantage of the Valkey Search. Okay, so what Valkey Search will do is that, okay, we got to get going here, so I'll fast track a little bit. So there's behind the scenes, it runs this FT for full text command, so it'll create the index with a number of dimensions, the same as your LLM. Then you will shove data in there. You have to store it as bytes. And Valkey Search will automatically index the documents with a specific prefix and the fields within those documents, like the ones you specify. Like you can still store a whole bunch of cache data there, or you can use Valkey for other purposes, but Valkey Search will only care about the indexes, the documents that you tell it to care about. And then you can run search. And if you're using Redisson, it's got really nice abstractions. For example, it'll like help you create the index, it'll help you run the queries, etc. Okay, let's do a demo. Okay. So semantic cache. Let's say I want to ask a question, capital of France. Okay, so see how it's thinking? What's happening behind the scenes is it's hitting my model, and it tells me capital of France is Paris. Great. Let's say another user comes along and types France capital. But before we do that, let's see how it looks in Redis or Valkey. So you see here that I created two keys. One is doc, which has the index and 16 kilobytes of vector, and I'm storing the input text. And the second key is the cache, where I'm actually caching the response from the LLM with a TTL. Okay, so France capital. Let me type it correctly. Okay, came back really quickly. If we look behind the scenes, we see there's no new content cached because capital of France and France capital are pretty darn similar. So it found a match to this index document and then simply retrieved this cache without incurring the second LLM inference call. Well, let's see how it can possibly go wrong. Another user comes along and types German capital. I think we just caused a geopolitical incident. Why? Because we set our similarity threshold to be very low. If we set it to be very high, see now it's thinking, that was the LLM call. And behind the scenes, we see now there is both the secondary index was created and stored, and a second content was cached. All right. Okay. Let's see. So I talked about Redis search with the Valkey search. Some references. I used Micronaut framework to build this. Caffeine, really nice library. Redisson, really nice library. Ollama for J simplifies integration with Ollama. And if you're interested, check out this article on Valkey search. It was published last summer. The new version has some new features. Cool. We got 2 minutes for questions.
Can you go back to the previous?
Which one?
The caffeine.
The URL.
The links.
Yeah.
Oh, the links, of course.
Upper layer and upper layer to upper.
So the Valkey search decides how many layers to create. So you don't have to worry about that. Just keep in mind that you got to use up a lot of RAM.
Yeah, but is it kind of doing some approximation from neighbors and identifying one node or?
So the Valkey search module, when you create this HNSW, oh, I probably should have showed you the code. Haha. So if you look at the semantic cache controller, you'll see here how it's actually, I'm generating all this embedding, and I know we're running out of time, so if you're really interested, just ask me, I'll send you the link to the GitHub repo. But basically, we're generating the embedding, we're converting it to bytes, and this is the first LLM call, the cheap one. Then, once I have the embedding in bytes, I can run my similarity search right here. So this is where I'm specifying my query, I'm specifying the options, and here's where, by the way, I'm doing the client-side or filtering for similarity threshold that is passed in. And I also have the code here to create the index on startup. So you'll see here that there's, for example, this rsearch, which you can easily double-click on and see that code. And you can see that there is ability to specify prefix and the fact that it's indexing hash fields, hash data structures, which field within the hash it will index. And then, for example, the number of dimensions, and I'm using cosine similarity here. All of this is super easily configurable via this library. Now, once I get the responses back, if nothing is returned from my VSS search, I then save the embedding, and I assume that my best result was the input string that user typed. Otherwise, if the search returns from VSS a match, I then just grab the very first one. And then I check the cache. So now at this point, VSS is done, and I check my cache, and then cache is just a really simple just get operation. So if the cache is found, I use it. If it's not found, this is the second expensive call to LLM to run inference. So again, you'll see all this Ollama helper code that just helps me do it. You don't need to use Ollama. You can just make HTTP requests, but I specify like which model I want, and I generate the response. And then I will cache the response that I got from Ollama for a period of time and return it. Okay, we have 1 minute left. What? Yes. So well, what you can do is you can store the vectors then. Like you don't care about the cache response. You can save memory. But if you can like somehow create relationships between these vectors, say, hey, vector A is very similar to vector B. Yeah, so that's a possibility for storing vectors separately from caches and potentially using different data structures. But they take 16 kilobytes. Like you saw the response from LLM, that's not 16 kilobytes of data telling me the capital of France is Paris.